with that being said, at any time, don't hesitate to interrupt me and ask questions along the way. So, where is West Virginia? If you aren't familiar with the U.S., we are that red dot on the left, and then as you zoom in, Morgantown is in that north central red dot right there. So that's where I'm coming from. Very hilly campus on the left when it's nice and green, and when it's grayer and a little bit of snow, we never get very much on the right. And that's our personal rapid transit system, which opened in 1975, and there's only about 5 transportation systems like it in the world. So as our campus grew, we needed a way to transport students quickly, and this is what they came up with. There's a lot of things to talk about there, but that's not our primary reason for being here today. We want to talk about research in undergraduate math classrooms. So SPEAR called for empirical research around these 7 dimensions of undergraduate classrooms. And specifically, we are going to talk about 2 of them. Number 2 on this list, selecting and sequencing content, and number 5, representing mathematical concepts and relationships. And this data comes from a much larger project. We had 5 instructors who were generous enough to say that, yes, we are committed to incorporating more active learning in our classroom, and we are willing to let you come and record our classes essentially every day over 1 semester. And then in the 2nd semester, we did just selected lessons. And so we have a very large data set. And as promised, I'm going to talk about 2 aspects of that. So first, let's talk about gesture and how we can use that to highlight key links in the 2nd derivative test. Well, why would I even care about gesture? Seems like you do it, but you don't think about doing it. Well, as it turns out, calculus instruction hasn't really changed in like 200 years. And there are over 300,000 students in the US alone who take 1st semester calculus each year. And it's one of the courses that has a very high failure rate. Somewhere between 40 and 60% of students will fail that course on their first attempt. And it becomes a major reason that they actually choose to leave STEM, whether that be math, physics, anything, but that it causes them to say, I'm going to change my major, I'm going to go do something totally different. So as instructors, it's on us to maybe think, how can we reinvent this and make it more relevant? What can we do differently? Gesture has great potential. It's free, which is a big thing, and it's easy to implement. Most of us have bodies that have hands that can do things. So we have this option available to us, so let's start exploring how we might harness that. As far as using gesture at the undergraduate level, there's not been many studies, very, very few. It does exist, but there's not many. There's a lot more at the elementary and middle school levels. Alibali, Hostetter, and Cook even have shown that teachers' gestures are malleable. You can get teachers to change what they do with regards to their hands when they're teaching, either by instructing them specifically to do something or to say, think about the gestures you make. So, and when they've done this, they have improved student outcomes. So we have reason to believe that mayhaps this would also translate as we work our way into higher levels of mathematics. So the 2 bigger questions I'm looking at are, how do teachers gesture naturally during instruction, and what is the added value of gesture to your students? So the larger theoretical framing is a semiotic bundle, which, if we're thinking about the words, the inscriptions, as well as the gesture that we're using when we're communicating mathematics. And then specifically, Alibali breaks her data down into linking episodes, where she's looking at segments of discourse in which teachers are making connections for students. Here's an idea, they're related, here's how they're related. How do we put those ideas together? And then do we make those links either just in speech or do we do it through gesture and speech together? So that's sort of the bigger picture in terms of framing. So what about the actual data? We've got these 5 instructors, as I mentioned. We're going to look at the lesson on optimization. The previous lesson was curve sketching, in which students were learning about a function, its derivative, its second derivative, and what that can tell you in terms of the properties of a graph. What's increasing, what's decreasing, where we have sections that are concave up, concave down. Then in this follow-up section, now we're using it in terms of an application. We're looking at, we want to maximize or minimize something. And in this case, all 5 of our instructors used essentially the same context, which was also similar to the first example that occurred in a textbook. You are going to maximize area for a given perimeter or vice versa. And in this context, they introduced the second derivative test. Prior to this, this formal piece of mathematics had not been introduced in the classroom. So we've taken each of these lessons, we've transcribed them, coded them for their gesture use. Some graduate students definitely assisted with that, making sure that when we were saying and talking about a gesture, we all agreed we were talking about the same kind of gesture. And looking at these lessons where the second derivative test comes in. And identifying them as unimodal or multimodal. Did they use only speech or did they use things beyond their speech, including gestures? So, we are going to look at 3 brief episodes from 3 different classes. So, as we watch this, pay attention to the gestures that the instructor is making and think about what is she highlighting? What might she potentially be giving to the students they wouldn't necessarily get from a textbook?
So here, f prime of c is equal to 0. Okay? What does the second derivative tell us? Concavity. What's the concavity right here? Down. This is concave up. So we have a derivative that is 0 or DME. DME is a little trickier sometimes. Okay? And if f prime, f double prime is less than 0. So this is this guy. Do you have yourself a map or do you have yourself a map? So this is concave down. So you get it. If your second derivative is greater than 0, that tells me concave up, that's this shape, and I'm looking at where the derivative is 0. That tells me I have what on my graph? A MEU. Okay? So the idea, you have a critical value, alright? And you can find the concavity. If it's concave down, you have yourself a max. And if it's concave up, you have yourself a min. Okay?
What did you notice? Take a minute, talk to your neighbor, and see, what did you notice?
I don't focus on one.
Oh, okay. You guys noticed.
Yes.
You're going to need like an indication
Also had to make sure she turns like the guys on this side could actually share Otherwise,
Oh, yes, that's right.
I just feel like you're looking at a page and you can easily explain, you're not necessarily giving it.
Yeah, okay, so like, in some sense, like, yes, she had.
the guy on the grey, the front of the right, got a lot of
I think that.
the others were silent.
I was surprised that she was not using the gestures two hands, like
Did you notice something?
when she's tracing the curve up and say this is concave down. I would use two hands to do this, or like one hand, like curved hand. But she didn't do that. She was just tracing the curve and she was showing the tangent.
Okay. What kind of things do we observe?
Well, I guess just follow the curve of the drawing.
Yes. Almost everything she's done has been grounded in the board in some way, shape, or form, right? And every gesture is referencing something on that blackboard, pretty much. When she stepped over to the side, there was a little bit of, if you've got something with a critical value, right, off to the side a little bit, but pretty much everything she's done is trying to capture the student's attention with relationship to that graph, right? And talking about the second derivative tells us something about its concavity, whether it's concave up or down. And as she's doing that, she's highlighting the pieces of the graph that are concave down or concave up by sort of generally circling a general area of the graph or tracing very specifically that graph, right? So, but almost everything she does is very much grounded in the board. Now, if you were just reading a textbook, would you get any of that? Probably not, right? So let's look at instructor B.
We're going to figure out what is the concavity when W equals 32, so our critical point. So technically, I want to look at F double prime at 32. Now, in this case, my second derivative is a constant, which is negative. If I plug in 32, I get the same thing, right? So I'm always going to get, for this example, this is always going to be concave, up or down? Down, right? So F double prime for of 32 is still negative 3/2, which is less than 0. So F of x is concave down. So that's where we have negative second derivative. We've got our frowny face, right? So we're concave down. And if we're concave down, and at this point right here, because we're, just look at this. Sorry. That's a big question for me. So at this point right here, local max or local min? Local max, how do you know it's also an absolute max in this particular problem? Because it's the only critical point, and we're concave down everywhere, so this has to be the absolute maximum.
So, this one looks different. The mathematics being communicated is still the same idea, but it looks different. There's definitely gestures grounded in the board, like we just saw, but there's also something where stepping aside from that and stepping out in front and talking about, we've got this local thing happening, and then making the connection to even absolute. And so there's something about sort of the relative sizes here. This is something local, like we're zoomed in, compared to the overall whole graph. So there's now a distinctly different element. And I'm not saying that either of these things is necessarily better or worse. They're just different. At some point we might be able to say something about if they're better or worse if we did some sort of controlled trial study, but that's not my purpose here. instructor C.
40 is 0. Now watch. The derivative at 40 is 0. When the derivative is 0, that's either this shape or this shape, right? The tangent line is 0, so we know at 40 it's either this or it's this. How can we tell which one it is? By not testing the first derivative, by testing the second derivative. Because the second derivative is negative, it's this, which means at 40, it's the high point here, which is a maximum. And does that verify the question we were asked, maximum?
And yet here we have a completely different sequence of gestures to indicate the same information yet again. This is unique in that this is the only instance, I believe, in our whole data set where we've got someone who is very explicitly drawing attention to their gestures. He actually says, watch, 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 before he starts this whole production, right? He wants to make sure that they are paying attention to the way that he is using his hands. He does, over on the right side of the board there, have a small concave down shape drawn. That just before that he's like, oh, it's negative, it's concave down. But for his explanation, it's explicitly through speech and gesture. And he wanted to make sure that the attention was on him. So yeah, it's something completely different. At this point, I don't know exactly what all this tells us, other than I know that there's something distinctly different that they get from that experience in the classroom than what they would get from, say, just reading a textbook. And so this is a quick tabular representation of each instructor, the links they made between, like, saying concave down means we have a max, and between the graphical and numerical representations, and whether they made them in speech and gesture. So it's very, as far as we can see, the landscape looks different just depending on the instructor. And that's okay. But they all made two links. And the first link being between the sign of the second derivative and the concavity, whether it be up or down. And then between having something that would be concave down or concave up and having a max or a min. And often those two came right in quick succession, as we saw. We have something, we have a second derivative that is negative, thus it is concave down, thus we have a max. And linking those three ideas all together. So, that's a piece of the data that I am particularly interested in, and that's my own personal work, and it's still a work in progress. But the other part that I want to talk about today, and I'm happy to talk about that at any time with anybody, is simple prompts and example generation. This is jointly at work with my colleague Vicki Seeley in the math department and John O'Boyer and Matt Campbell from our College of Education. And so here we took a communities of practice approach to our data. So communities of practice approach, we are looking at students positioned in the classroom to be competent participants, engaging in authentic mathematics, seeing themselves as people who do mathematics, and they have the opportunity to experience meaningful ways of doing and constructing mathematics. And this means that we aren't just looking at, are they doing group work? Did you give them a worksheet and ask them to work in groups? That's not what we're talking about. We're talking about getting them to do more intellectual lifting. And so the substance of that participation is equally important, not merely practice, but engaging meaningfully in mathematical thinking and contributing to a collective effort. So the data we used for this was the mean value theorem. There it is, as stated in their textbook. We chose this because it's not a coordinated lesson. They are free to do whatever they want when teaching the mean value theorem. And it spans at most 2 days of class. Generally, it's only one class period. Sometimes it might get started not quite at the beginning of the class and need to spill over to a second class, but it's generally very short amount of time that's taken in the classroom. And so we watched these lessons, and initially we were just trying to, again, with this idea of we want to see how much active learning is happening in our classrooms. We said, what kind of activities are they doing? Are they doing group work? Are they looking, at something individually? Is it just straight lecture, like I'm doing to you right now? What's happening? And what we saw is that we had classes that may have had similar participation footprints. It's like students are doing something for X amount of minutes and instructors are doing something for X amount of minutes. But there was still something that was qualitatively different about those classes. And so we wanted to identify what made them distinctly different and made some of them feel better. Now, we aren't saying that any of these were bad lessons. They were all good, well-founded mathematical lessons, but what just made some of them feel different, feel better, as it were. And it came down to the depth that the lessons went into. So our 4 emergent themes that came out were who generated the example, who evaluated the example, how precise was the example, and how was the example used. All of these lessons were very example-centric. Should have said that before. So, we're going to look at Instructor A. Instructor A is not the same Instructor A as in our previous set of videos. They changed between data sets, and so just know that Instructor A in this case is not the same Instructor A we had before. The instructor started, drew the graph on the left, and said, what's a secant line? And the class was saying, you connect your endpoints, something along those lines. And so she had this graph on the left and said to the students, all right, what I want you to do now is take a couple minutes and see if you can find any places where the slope of the tangent line to the graph and the slope of the secant line would be the same. And so she walks around. Students are on their desk, they've got this sketch, making sure everybody knows what they're supposed to be doing. Takes about 2 minutes of class time, then goes back up to the board and says, okay, it seems that most of you found a point, and she used her marker as a tangent line, placed it on the secant line, went up, identified those 2 points, and said, we have, in this case, 2 values, 2 places where we have a slope of a tangent line that is the same as the slope of our secant line. Then, she says to the students, your job is now to find several more graphs that do have this property and do not have this property. Go. And so, the students go, and they are working. They end up working on this for about 16 minutes. After about 4 or 5 minutes, as the instructor's walking around, making sure the students are coming up with both types of graphs, she sees one of the groups has this graph on their paper, and she goes and puts it on the board and says, I want to make sure everybody talks about a graph like this. It's a horizontal line. It's up there. She lets them go for about another 2 minutes. And then she says, did everybody talk about this? And you see all the nodding yes. And she says, so, is there a point where the slope of the tangent line would be the slope of the secant line? And there's a group that says, no. Right away, no. But then there's a group on the other side of the room that says, yes. And the students start talking to each other. And the group that had initially said no changes their thinking very quickly. And they come to agree that yes, in fact, there is. There's an infinite number of points. Then they are allowed to continue coming up with more examples. And the instructor says, I want each group to go up and put at least one of their graphs on the board. And one of the graphs that does not have that property of slope of the secant line and slope of the tangent line being the same. Being able to find one of those points. So the students go and they're all putting graphs on the board. And so here's our nice collection. Ultimately there were 10. We're going to pay attention to the one that's in the upper right corner there and the lower left corner there now. And so there's this graph in the upper right corner that starts out like this. And she asked the students, do all of these examples violate this property of being able to find a slope of a tangent line being the same as the slope of a secant line? And one of the students says this one does not. So the students are doing the evaluation process. And one said, but wait, but it does outside the interval from A to B. And so they had so there's this question about, does this interval matter? And so they decided that yes, you have to only look at between A and B. And then this question, so the graph gets modified to erase everything outside the interval from A to B. But it's still got this hole. And so a student starts talking about, but wait, the limit exists over there. So does this work or not? And so the students start discussing, and ultimately they bring it back to the definition of derivative and limits of tangent lines. And they start talking about what happens from the left, from the right. What if we put in a value but not at that hole? And they determine, in fact, that this would be an okay case where we can't actually have that tangent line. And it leads to a nice discussion, rich discussion about why that condition on the function being differentiable is important. The other thing that came up in this discussion is precision. So the students had drawn a graph like the one on the left. And so in looking at this, what ends up being the case? The this did not get picked up by any of the students. So the instructor said, well, if you put that on a test as something that does not have this property, would you get it right or wrong? I think I understand the intent that you had, but in this case you would get it wrong, right? And so then the graph was modified to look like the graph on the right. Because now we have a graph that would not satisfy the property that we were interested in. So this was a case where the example was also used to illustrate something where the precision of what you're drawing, even if your intent is correct, that precision in mathematics can make a big difference. So, all of these graphs on the board, they've had these discussions about even nice things about limits of tangent lines and why it's important to be differentiable or not differentiable. So the instructor says, what do all these have in common? They're not continuous, they're not differentiable. Whereas that first graph was nice, it was continuous, it was differentiable. So we now are at a point where the instructor was able to write the mean value theorem on the board in all its formality. And one of those graphs that was on the board also was the focal point for why that continuity is important on the closed interval versus the open interval for differentiability. So, what did all of this tell us about this lesson compared to some of the other lessons? Who generated the example? In this lesson, every example, aside from the first one, was generated from the students themselves. In the other lessons that we saw, there was a very clear sequence of examples that the instructor had planned out and presented to the students. As a result, who interpreted the example changed. When the students were the ones generating the examples and putting them up on the board, what ultimately happened? The students were much more readily to engage with saying, what about that one? Wait, and doing the evaluation. But when the instructor gave the example, it was like, if you've given it to me, of course it's fine. I don't have to do any thinking. I don't have to do any heavy lifting. And there were also some cases where the instructor would say, can you give me an example of something, and the student would say y equals x, or points and something with a point. And so, the instructor interpreted exactly what that would mean and would draw the graph, as opposed to the students actually doing it. So, I've already hinted at this as who evaluated the example. When the instructor gave them, it was like taken as word. This is good compared to the student. Now, that's not to say a student who's not listening to a lecture wouldn't necessarily be evaluating things, but we have no evidence of them actually doing that evaluation. All we know is it was presented, there were no questions, no follow-up, so we don't know what was actually happening on the student side. How was the example used? For most of the classes, it was the instructor presenting one example, this is in existence, here's a graph, this makes it work. Compared to being able to say, can you discover something about all of these graphs? What do they have in common? Constructing that mathematics. Addressing common misconceptions, as well as preparing for a test. This is the kind of thing you need to make sure you're careful about if you're sketching. Preparation for the test came up in all of the classes as well. So the richness of the example. So for example, this nice horizontal line, what makes it so rich? Why did the instructor make sure that everybody talked about it? There were 3 distinct things that easily came up as important. Addressing a common misconception. There was a group that immediately said no. There was infinitely many c-values, so what does that look like? What does that mean? And then Rolle's theorem, which is a very special case. Sometimes it's presented before the mean value theorem, sometimes it's presented after as a special case, depending on the textbook. But it also gives you a way to talk about Rolle's theorem. And a lot of that discussion is dependent on the instructor facilitating those discussions. You have to be able to ask the students questions to get them to think about, or making sure that they do talk about some of these ideas. And then the rigor. So this example, one of the students came up with, was the touch point for why continuity is important, and that those closed endpoints on that condition. And instructor C actually did incorrectly claim that a closed interval was necessary in order to compute the average rate of change. But instructors B, D, and E didn't even address why there was a closed interval. Instructor B even had this graph as one of her examples that she presented, but just didn't use it and leverage it to present that information. Now you're probably thinking, all this time taken for students to go and generate examples, it's going to take way more class time, right? That's what you think, right? Instructor A took 42 minutes of class time for the mean value theorem. Instructor E had the least amount of time at 38 minutes. Instructor B had the most at 53. So instructor A is right in the middle. It wasn't really any extra time. So, in summary, the focus is not only on just doing something, but it's the depth of the mathematics that you get to bring out, the authenticity of the task, the opportunities for the students to engage and wrestle with the ideas themselves, and constructing the mathematics. They were able to figure out the hypotheses of the mean value theorem by looking at all these examples that they had constructed themselves. And that was really powerful. My guess is they've remembered that longer than somebody who just saw a presentation of, here's the examples on why it works. And they also led to richer and more rigorous discussions. They were the only class in which they really dug into even the limit ideas from much earlier in the semester about why these things were happening. So it's really, as far as we're concerned, we think it's really powerful. And it was a really simple prompt that got them to this level of engagement. And so just as we're thinking about active learning, we're trying to figure out how do we do more of this? How do we bring more of this into our classrooms? And hot off the presses. This article literally just came out in the Journal of Mathematical Behavior. And so we've got, if you're interested in it, I will happily send it to you. But that's got all the nitty-gritty details in it. And so with that, questions. And thank you for coming out on a Friday afternoon. It's a nice day.
So